Hi, let's take a look at an example of applying the ideas of centripetal acceleration to a real-world problem. Now, whenever you're turning, as long as you can find a force that turns with you, then you can generate the acceleration that you need in order to change your direction. Well, one way that we could create a force that changes with us is to take a roadway and bank it. It's kind of like a ramp that extends around in 3 dimensions. So if this arm here is representing the track as a car's coming out of the board, then it curves around, and by the time I get back to the board, it's heading in towards the board. Now, if I were to take a look at the forces, I don't necessarily need friction, because I know that car's in contact with the track, I get a force that's perpendicular to the track. And because we're on a planet that has gravity, we have a weight pulling that car straight down towards the center of Earth. Well, those two forces can't cancel out. But that's great because we don't want them to cancel out. We need an acceleration in towards the center of the turn, and the center of the turn is going to be directly in towards the center, so as this car is drawn directly towards the right. And as we would normally frame Cartesian directions here, if we're saying gravity's in our negative y direction, our acceleration would be in our positive x direction. So as long as that normal force rotates around in that circle, we always have that x component, or whatever component we want to call it, pointing inward, changing the motion of that car. And to solve for the size of that centripetal force, the x component of that normal force, well, I can look at what results from adding my weight to my normal force. So by putting the normal force at the end of my weight vector, I form two sides of what would be a right triangle, where the angle between my weight and the normal force is the angle that the ramp is tilted above the ground. That's the angle that the normal force tilts away from, straight up and down. And this x component is opposite the angle of banking. I presumably could easily find the weight of the car, so the tangent of that banking angle is my opposite side divided by my adjacent side, the weight. So that means then that my centripetal force has to be equal to the weight, the mass times the strength of gravity, times the tangent of the banking angle. And since with centripetal force, the size of the force is the mass times the speed squared divided by the radius of the turn, then the tangent of the banking angle is going to be equal to the speed squared divided by the strength of gravity and the radius. So say we want to build a racetrack where we have no friction, but we want a car to be able to travel at 200 miles per hour around a 180-degree turn that travels a distance of half a mile. So essentially, this is like the 180-degree turns in roughly the Indianapolis Motor Speedway size distance. So half a mile is about 800 meters. And since I don't know the strength of gravity in miles per second squared or miles per hour squared, 200 miles per hour, I can multiply that by 0.447 meters per second for each mile per hour, works out to be 89.4 meters per second. So the tangent of my angle is my speed, 89.4 meters per second, quantity squared, divided by gravity, which has a value of 9.8 meters per second squared, and my radius. Well, this isn't the radius. This is the distance we drive along the track. But if we think about it, if we're turning 180 degrees with the same radius, we've gone through half a circle. So if I drive the whole perimeter of a circle my distance s would be 2 pi times the radius. So to go halfway around, my distance is pi times the radius. Or my radius is the distance it takes me to make my turn divided by pi. So I'm going 180 degrees, or pi radians, in 800 meters, divided by that pi radians, means my radius is 255 meters. So that gets thrown into the denominator, and square that, divide by the product of those two numbers, I get a tangent of my angle that's equal to 3.21. And remember, tangent, there is no upper limit to the value of the tangent. It's some number between 0 and infinity in terms of magnitude. So the inverse tangent of 3.21 gives me a banking angle of 73 degrees, which granted is pretty steep. And one of the things that would happen is if this car were to come to a stop on that track, there is a very good chance that it would end up rolling down that sort of embankment. Usually in designing curves, designing racetracks, we try to avoid making nearly vertical walls. So typically a severe angle of embankment might be around 30 degrees. And under normal conditions in commercial air traffic, 30 degrees is about the limit that you can get. But even 30 degrees is still a pretty steep turn that you have. So in real race cars, you need to have friction plus that normal force. So banking lowers the amount of friction you need so you can maintain higher speeds while traveling through that turn. Thanks for watching.